in this video we're going to be doing a quick wrap or a recap on integer exponents. So because this is going to be useful in the upcoming videos, so a quick reminder. Say we have an exponent b to the negative n. This is equivalent to b to the power of 1 over bn. That's what the negative exponent is. And b cannot be 0. So, another thing, just some rules. A over b to the power of negative n is the same, based off this logic, is 1 over a over n, a over b to the power of positive n, and 1 over that is just b over a to the power of n. And that's also where a and b cannot be be 0. And also, keep this in mind, anything to the power of 0 is automatically 1, and b cannot equal 0. And that actually, we can actually prove really quickly. Say we have 10 to the power of 6 divided by 10 to the power of 6. When you do division, exponent division, so anything over itself, like 1 over 1 is 1, 2 over 2 is 1, 3 over 3 is 1. So 10 to the power of 6 to 10 to the power of 6 is also 1. But if you were to write this out, 10 to the power of 6 minus 6, which is 10 to the 0, you already know this is 1, so it's 1. You could replace this base and this exponent with anything, and you'll end up through this logic equaling 1. So remember this. What else? Yes, so we have the exponent multiplication, b to the power of m, b to the n, and that'll give me b times m times n. I wrote that wrong. So when we're multiplying exponents, we add the exponents, same base. And then same with b to the m over b to the n. We get b to the m minus n. Remember that one too. And also, that's multiplying, dividing, and then we also have b of m, b to the power of m to the power of n is equal to b times m times n. So that'll just multiply inwards. Okay. Forget about that one. So, let us look at some, I guess, ways we could find these things useful. Let me just give this some space here. So say I had 5 to the negative 3. That from our previous understanding is 1 over 5 to the 3, which is 1 over 5 times 5 times 5, which is 125. And there you go. That's what that is equal to. And if we do, say, negative 4 to the power of negative 2, that is equal to 1 over negative 4 squared, which is equal to 1 over negative 4 squared is positive 16. 3 to the power of negative 4. That is another ways that we could write it if you didn't want to take the negative downwards. Actually, wait. I wrote this wrong. In this case, I have the negative 4 in a bracket, but here I have the whole expression as a negative, so no bracket. So here, it's like this, technically, but imagine there's no brackets. So here it will go positive 4, which is the same as writing. Let's do something like this. 2 over 3 to the power of negative 3. And as we remember from doing so many of these, that is the same as I can flip this fraction, or I can evaluate it right now. So this will go into here. 2 times 2 times 2 is 8 over. And then when you flip that fraction, because that's the base, so this is the logic here. If you were to write out every step, let us do one more. Let's do so let's use our good old exponent rules to solve this step by step. And the numerator, same base for multiplying, so we have correct. Here we have a power of a power, so we're going to multiply. So 3 to the 5 plus negative 2 is 3. And then denominator we still have the 3, and then the negative 3 times 2, so negative 6. And there we have same base. Now we're dividing. So we're left with 3, and when we divide, we subtract. So that'll leave me with 3 subtracting negative 6, so 3 plus 6. 3 to the 9, which is the same as saying I did not do this in my head. I had a calculator. So that is integer exponent recap for us, which will be useful for us in the future. So come up to speed with these things. And we will work off of this when we look at things like exponential decay or profit interest growth or whatever. But yeah, stay tuned, and I shall see you in the next one. Okay, so in this video we're going to be looking at rational exponents, and so we're hoping in this investigation we're going to basically try to we're saying x cubed. And the area of one of its sides can be x squared. You know, x times x, and x times x is the volume. So, what we want to do here is basically from our exponent logic, and everything we know about exponents is represent x in the form or like as a expression of its volume or its area. So let's just try one. I know a equals x squared. So I basically want to represent x in a way, or like isolate x and represent x in the form of a. So one thing we can do is basically, the quick way to do this would be to square root both sides, and you're left with x equals the square root of a, which is also x to the power of 1 over 2, right? But if you wanted to do the full algebraic way, here's how you would do it. You can say x is equal to a to the power of n, and I don't know what n is yet, but I know that a is equal to x times x, which, so by this logic, if a equals, if a of n equals x, and I have a equals x times x, so that means a is equal to a of n times a of n, a to the power of n times a to the power of n. And our exponent laws tell us that we're going to when we're multiplying exponents, we add them. So it's going to be n plus n, which is also a to the power of 2n. Therefore, I can say that on this side, when we have 1, a to the power of 1 equals a to the power of 2n, now I'm left with this expression. So with 1 on one side and 2n on the other side, I can write this 1 equals 2n. And this expression, or this relationship, we can exploit it to find n, to isolate for n here. So if 1 equals 2n, that means n equals 1 over 2 if I divide both sides by 2. And therefore, x is equal to a to the power of 1 over 2. Oh yeah, sorry. That might have confused somebody. Somebody was confused. And you know, that is the same as writing that square root is basically saying to the power of half. And you know what? Let's look at the volume now. If we were to do it with the volume, so x is equal to v to the power of n, and I know that v is equal to x times x times x, and if each x is v to the n, that's the same as writing v to the power of n plus n, which is, and again I have 1 equals 3 n, so n is equal, therefore x is equal to v to the power of 1 over 3, or cube root of v. This is the wrong way to do it, but the correct way, as you see here. But eventually, as you continuously do these problems, you'll see that very quickly when you have, say, v equals x to the power of 4, you can just say, oh, I'm gonna do, when you want to bring this over to the other side, it becomes 1 over 4 equals x. It's very intuitive, like you'll get into the habit of doing it. So let's do some problems. Let's say I have, and I want to evaluate this in radical notation. And if you remember radicals, well, you obviously do remember it. So let's use our exponent logic. So we remember this is 1 over 49 to the positive 1 over 2. And, you know, 49 to the power of half is the same as, say, root 49, which is 1 over 7. Simple as that. Let's do this one. Negative 8 to the power of 1 over 3. You remember how to do that. We have 1 over 3 is the same as our cube root. And we know that we're going to end up with negative 2. One thing that's very tricky here, that you have to wrap your head around is you can take the square root of a positive number. So you can do of any positive number and you end up with a positive or a negative number. That's fine. But a cube root, if you try taking the square root of a negative number, you're going to end up with an imaginary number. So that's something that we're going to learn much later. But yeah, keep that in mind. And when you do cube root, whatever the sign is, it's going to stick. So if you take the cube root of a positive number, you can end up with a positive number. If you do cube root of a negative number, you're going to end up with a negative number. And that is because, say in this case, we have a negative 2, right? Negative 2 cubed is basically negative 2 times negative 2 times negative 2. This times that will give me a positive 4. But I'm multiplying it by a negative 2 again, so I'm going to end up with a negative 8. So cube root of this will give me a negative 2. So remember that. And that goes for every odd root that you want to do. So even if you were to do a 5, you end up with the same sign. So yeah, keep that in mind. Let's see if I can get another one in. Say 10,000 to the power of 1 over 4. Let's do a fourth, 10,000 to the power of 1 over 4. That'll give me quad root. And so, basically, do I have a number that'll go multiply itself 4 times and give me 10,000? So, let's look at this. I believe it's 10. 10 times 10, it gives me 100. 10 times 10 times 10 will give me 1,000. And then another 10 this 27 is also the same as saying to the power of 1 over 3 times 2. So, if I was to break this down, then I could break this into a power of a power. So I'm left with 27 squared, like that. So that expression here will give me 27 squared cube root. Alternatively, I could go the other way. I could leave 27 here and do the cube root and then square it, which is and I think this is easier than that. 27 squared is a huge number, which is 729, and that'll give me 9. But here, cube root of 27 is 3. So, same. I'm good there. I wonder. Let's try some more. Just to kick this into our habit. Maybe time for a solid color change. Let's do negative 27 to the power of 4 over 3. And we're going to break that down again. Times 4. So that'll give me that's going to be negative 27 cube root to the power of 4. Cube root of that is going to be negative 3 to the power of 4. And I'm going to get 81. And why this turned into a positive is because negative 3 times negative 3 times negative 3 times negative 3. These two will multiply and give me a positive. Then I'm going to multiply into this negative and give me a negative. Negative times this negative is going to be a positive. So, the even amounts of times that I'm multiplying this value is going to give me a positive, and negative, odd number amount of times is going to leave me with a negative. Let's do another one. Let's do 16 to the power of negative 0.75. You have to recognize that that's a fraction that I can represent negative 3 over 4, which is the same as saying 1 over 16, 3 over 4, which is also the same as saying and I know that that is going to give me a 2. Let me put that on the outside. So let me write it here. So that should give me 1 over 2 cubed, 1 over 8. Yep. I agree, this is very easy. Let's do maybe something a little more complicated. Let's do 8 to the power of 5 over 6 times square root of 8 over 8 to the power of 5 over 3. So, let's take this step by step. First off, 8 to the power of 5 over 6. That's 1. That 8 is to the power of half. That one is okay. 6. Wait, did I get that correctly? 1 over 2. Wait, what is that? 5 over 6 plus 1 over 2 is the same as 5 over 6 plus 3 over 6, which is 8 over 6. Okay, 8 over 6 is going to give me 4 over 3. Okay, that's what I want. Over. So now I have this evaluates to 4 over 3. So I have 8 to the power of 4 over 3 divided by 8 to the power of 5 over 3. Dividing exponents is going to give me a subtraction of the exponents, so 4 over 3 minus 5 over 3. So I'm left with 8, I'm left with negative 1 over 3, which is the same as saying 1 over 8 to the power of 1 over 3, which is the same as saying 1 over cube root of 8, which is 1 over 2. Wow. All that evaluated to 1 over 2. Yep, I deserve a break. So, that has been some rational exponents for us. I hope I didn't lose anybody anyway. But yeah, hope you enjoyed that. And I shall see you in our next video. Okay, so in this video I'm going to be simplifying algebraic expressions involving exponents. So let's look at a sphere that looked like a head, but no, it's a sphere. So let's look at the formulas for a sphere. The surface area of a sphere is 4 pi r squared, and the volume of a sphere is 4 over 3 pi r cubed. So now I want to do this. I want to find this expression, surface area over volume. This basically represents the surface area to volume ratio, in which, well, you'll see what we do. But the point of this being is that we have exponents in this expression, and now I want to simplify it. So from our previous videos and whatnot, we know that we can start canceling things. So I have, well, let me write this out a little bit more. R squared is the same as saying R times R, and in the denominator I have a 4 times a 1 over 3, which gives me 4 over 3. I have a pi, and then I have an R, R being a radius. So now let's start canceling things out. I have a 4 in the numerator and a denominator. Gone. My pi is gone. I have an R, I have an R, I have an R, I have an R. So I'm left with 1 R and a 1 over 3. So I'm left with 1 over 3 times R. So R over 3, which will become there we have it. That is us simplifying an algebraic expression involving exponents. That's the end of the video. I'm kidding. This basically in math terms represents the ratio from between surface area and volume is 3 over the radius. We don't need to do anything with that. I was just using that as an example. What we are going to do is something much more fun now. Let's look at this. Let's say I have 2x to the negative 3 y squared This looks great. So let's start doing this one step at a time. So let's do the cubed, the exponent out here first. So let's bring this in power of a power. So that's technically, you don't see it, but that's to the power of 1. So we have 2 to the power of 3. And then we have x to the power of negative 3 cubed. And then we have y squared, which is also cubed. And then in the denominator we have x cubed squared. And we also have y to the negative 4 squared. So if we were to write this out again, we're going to have 2 times 2 times 2 is 8. And then we have x to the power of negative 3 times 3, which is negative 9. And we have y to the power of 2 times 3, which is 6. And in the denominator, x to the 3 times 2, that is x6. And then we have y to the power of negative 4 times 2, negative 8. So let's start doing our division. So our 8 has nothing that is being divided by, but we have exponent x in the numerator and denominator. So their exponents can actually subtract. And then we also have a y, which their exponents can also subtract, in which I am left with our 8 x to the negative 9 minus 6, which is negative 15, and my y 6 minus negative 8, which is 6 plus 8, so 14, and my negative exponent. It's okay to write it like this, but if you want to get rid of the oh no. There. This big scary guy is now this guy. See, it's simple. So simple. Let's do another one. Let's try this expression. Say I have an expression, a very big one. Let's say x to the power of 2 n minus 1 and 3, sorry, x to the power of 3 n, actually that's a plus sign, 3n minus 1 over x to the power of 2n minus 5. And now I want you to substitute x equals negative 3 and n equals 2. And now solve for this. What does this expression come up to? I don't know why I'm telling you this when I have to do it. So let's do this. So our x is 3 to the power of 2 times 2 plus 1. Yep. And then, oh wait, negative 3, sorry. And then we also have negative 3 to the power of 3 times 2 minus 1 all over negative 3 to the power of 2 times 2 minus 5. So we're left with negative 3. 2 times 2 is 4 plus 1 is 5 times 3 times 2 minus 1 is 6 minus 1. It is 5 over negative 3. 2 times 2 is 4 minus 5 is negative 1. So now I can add the numerators, or I can actually evaluate this. 3 times 3 times 3 times 3 times 3. I don't know how many times I said it, but that's negative 243. Negative 243. And that's just over 1 over negative 3. So 1 over negative 3. If I punch this into my calculator, I should get 177, 147. And that is what that comes up to. And I know you might be thinking, when am I ever going to use this? I don't know, but I do know how to do it. Yay. So yeah, let's tackle this again. Except now, I'm going to, instead of plugging these numbers into all this and solve them, I'm going to evaluate this. Like, simplify the equation first. So let's do that. So first, let's do the numerator, x. So if I'm multiplying these two exponents, I'm going to add those. 2n plus 1 plus 3n minus 1. So I'm left with x to the power of, so 2n plus 3n is 5n. 1 minus 1 is, okay, 0. So I have x to the 5n. And now the denominator, I have x to the 2n minus 5. So now I can divide the exponents, which means I'm going to subtract them. Which means I have x minus x 5n minus 2n is 3n minus negative 5, so plus 5. So now I can plug in these numbers. X equals negative 3, n equals 2. Negative 3 to the power of 3 times 2 plus 5, which is equal to 3 times 2 is 6 plus 5 is 11. Negative 3 to the power of 11 is also what a coincidence. So yeah, that was just to show you how simplifying the expression before solving can save you so much time. let's do another scary one. So let's do 27 a to the negative 3. Let me write it again. 27a to the negative 3 times b to the power of 12 all to the power of 1 over 3 times 16a, divided by 16a to the power of negative 8 times b to the 12 to the power of half. So let's first bring in the power of a power. So 27 1 over 3, and then I have a negative 3 over 3, and then I have b 12 over 3. Denominator 16 to the half, a to the negative 8 over 2, b to the 12 over 2. And look, it's coming together. So I got 27 to 1 over 3, which will give me a 3a to the power of negative 1. And then I have b. 12 over 3 is 4. And then I have square root of 16 is 4. A to the negative 4. And b to the 6. And there we go. Now I can just rewrite this. I got 3 over 4. A is going to be negative 1 minus negative 4. And then I have b, 4 minus 6. So I have 3 over 4. So negative 1 plus 4, that's a to the 3, b to the negative 2. Or in other words, I can bring the b down and write 3a cubed over 4b squared. Simple as that. You know what? Maybe I can do one more. I don't want to use a whole new sheet. So let me just use it here. Right here, I'm gonna use it. Let's say I have oh no, I wrote that wrong. Let's do okay, my brain is not working. Not uncommon for math class. Okay, now we're gonna have some fun. So let's first rewrite this in terms of proper, like I want to clear up these square root signs. I'd rather just have fractional exponents. So I'm going to put x. So remember, root 5 of x is the same as x to the 1 over 5. So we already have an 8, so it's going to be 8 over 5 over x 3 over 2. And I still have my cube there. So the first thing I can do now is subtract these. 8 over 5 because I have a subtraction here. So 8 over 5 minus 3 over 2. Let's do the fraction math. I'll multiply that by 2, 16 over 10. Multiply that one by 5. Minus 15 over 10. So I'm left with 1 over 10. So x to the power of 1 over 10 cubed. And if I multiply that in, 3 over 10. And that is the same if I move it back into the square root. Boom. Well, just turn math upside down on us, and I hope I didn't cause too much pressure or pain. That has been I don't know what I'm doing here. Solving algebraic expressions involving exponents. And yeah, I hope that was helpful. And that's all for this long video, and I shall see you in the next one. Okay, in this video we're going to be looking at the exponential function and its transformation. So, a quick recap: the exponential function looks something like, well, it's something like that. So now we're going to be looking at transformations of this, like we did for our quadratic function and even the our linear one that we did a while back. So we're going to be looking at this function, y equals negative 2, 3 to the power of x minus 4. So right away, our parent function is going to be y equals 3 to the x. So if we were to draw that, at 0, at x equals 0, our y value will be 3 to the 0, which is just 1. And then at 1, 2, 3, 4, 5, 6, 7, 8. When x is equal to 1, 3 to the 1 is just itself. And then 3, 4, 5, 6, 7, 8, say 9. That would be somewhere here. And if you put 3 to the negative 1, you'd get like a very small number. So it'd be somewhere here. And it would just continue becoming a decimal number. And it would go all the way. It would just keep getting smaller. So So, how are we going to make this y equals, well, let me use a different color. Let's do now y equals 2. So whatever our y value was, now it's going to have a vertical stretch. So at 0, at x equals 0, we had 1, which was here, but now it's going to become 2. So our point will be here, and our 3 point will now go to 4, 6, and everything similarly like that. But also it'll still come back like that. But again, we have this negative sign, so actually let's do flip it on the x-axis, because whatever that value was now, it's going to be on the negative side. Oh, that way. That's very bad. But I try. Let's do now. We're going to do the movement on the x. So now we have an x movement. So this x minus 4 is in fact going to be a movement on the x-axis, but instead of, you might think it's going, like when I have a negative 4, x minus 4, you think it would go that way, but in fact it's going that way 4 places. So here I am. And like, you could actually like plug this in, like say you had y equals 3x and also 3x minus 4. When x is equal to 0, our y value is going to be 1. When x is 0, our y value is 1. But now we're going to have a minus 4 instead of, well, that's not 3x, it's 3 to the power of x. 3 to the power of 0 is 1. But now this is going to be 3 to the power of negative 3, which is a very small number. So instead now, if I would have to plug in x to the power, I would have to plug in 4 for x to get 4 minus 4 equals 0 to get a value of 1. So in hindsight, where I had this 0, 1, now I have to have, 0, 1, now I have 4, 1, which is all the way here. That is why this horizontal translation moves that way. And again, if you had plus 5 there, or plus 4, it would move the opposite way. So yeah, we have our reflection on the x-axis, we have our stretch, we have our horizontal movement. That's a lot of different moving pieces. So let's try one with with one more addition. Say we have y equals 4 to the power of negative 2x minus 4 plus 3. So, let's look at this. First, let's draw out our 4x. That's going to be somewhere 1, 2, 3, 4. So just approximate. Y equals 4x. But now I want to do, well, first let me rearrange this formula. That 2x, I can actually factor out the 2 and be left with x plus 2. So we have that. So one of the first things that I can see that I can do here, I have the x to the 4. Now I have the x values being multiplied by a negative 2. So when I have a negative in the exponent, now I have a reflection on the y-axis. And now that I have a 2 here, when you have a 2 here, that means you're going to have a compression of a factor of a half. So now our value is going to become, for one, it's going to flip onto, let me use a different color. So now this is going to be like that. So you can see that this one is closer to the line than that, because that is equal to y equals 4 to the negative 2x. So what else do we have? We have our we're left with this, sorry. So now we're going to do our, I forgot that I factored out the negative 2, so 4 to the negative 2 times x plus 2 plus 3. And this one, we can look at this right here. Remember our x being shifted. That's going to be 2 units to the left. If we add 2 here, that means we're moving to the left. Previous example, we subtracted 4. We moved over to the right 4. So we're going to go 2 units that way, and then we're going up 3 units. So 1, 2, 1, 2, 3, so somewhere there. 1, 2, 1, 2, 3. Say something like that. And that is my y equals. I'll be honest with you, I didn't think I could pull that off. But yeah, step by step, logic by logic, and we will survive. So yeah, that has been this video we're going to be applying the exponential function, so there's really only two types of problems that you're going to be using exponential functions. So that's going to be growth and decay. These are going to haunt you for many years to come if you choose to go into something math related and in chemistry. Just brought up a bunch of memories, so we're going to say that in the year 1996 we have a population of 35,000 in a city, right? And it has an annual growth rate of 8%. And now my question is, how long at this growth rate will it take for this population to double? So what we're going to do is use a formula, and our formula is going to be let's see. Okay, let's go with this. So, this is basically what you need to understand. This is a growth or even a decay formula. So, for the population to grow 8% from 35,000, if you were to multiply it by 1.08, that's basically giving it the 8% growth rate. You're saying that it's going to become 37,800. That's an 8% increase. And for it to go up again for 8%, you have to multiply it by 1.08 again, and you'll get 40,800. So now the question is, how many times it's going to take? How many times do I have to multiply this for this value to double to 70,000? Right? So, let's see. That's why in this formula we have n. That's the number of times we have to multiply this 0.18, which in fact means years in this problem, because we started 1996 and then every year we multiply by 8%. How many years it's going to take if each year is 8%? So we're going to multiply it by 1.08 n number of times, and I need to figure out what that n number of times is. But I know that my population is going to be 70,000. I need that. So in this problem, if you were to continue doing it, then you would have basically 69,965 as a solution when you have n equals 9. So if you plug 9 in there, you end up with that. Or you could solve for n using algebra, and that would just be 2 equals 1.08 n. And then you could solve for this, but I don't think we've covered how step at a time, but that's just an intro to this. So 9 years means by 2005 the population will double, just to give closure there. So now we're gonna look at a decay problem. We looked at growth, let's look at decay. So say we have, let me use a different one. 200 grams of some sort of material. Let's say it's plutonium or something. And the plutonium has a half-life of 138 days. What half-life means is that every 138 days, this will shrink by half. So after 138 days, this will become 100, then 50, then 25, and so on, every 138 days. So now we're gonna model this the exact same way. The mass that's left over based on our time that has passed by is our original amount, 200 times half, because that's what our exponent is going to be in the last one. We were growing by 1.08. Here we're decaying by 1.08. So 200 times 1 over 2 is 100 times 1 over 2 is 50. So how many times we're going to multiply this is going to be raised to the power of how many half-lives we're going to go through. So, but in this case, we're going to have this. So, one thing to understand is T is days. So, the question is, after 5 years, how much is going to be left over? So first what we need to do is say that, okay, in 5 years, 365 times 5, 1825. 1825 goes into our number of days. Why is that divided by 138? I'll tell you why. Because every 138 days, we're going to divide this. Sorry, every 138 days, we're going to multiply it into there. So, out of 1825 days, we're going to divide it by 138, and that'll give me how many times in this span of 5 years I'm going to have half-lives. How many times is this going to reduce by half? So, when you plug that in, 1825 over 138. Then you're left with, if you punch this part into a calculator, you actually get like 0.000104, which means you're only left with 0.021 grams left. After 5 years, you started off with 200 grams, and now you're only left with 21. So, another question here could be, oh, instead of finding out how much is left in 5 years, I could ask you, how long would it take for this 200 grams to become 110 grams? It's simple. Just plug in 110, 200. And solve. And now, again, I don't know if I showed you that part. But yeah, 0.55 equals 1 over 2. And then we can solve from here. but I would not. Well, we'll circle back to this method here. That is, in a future video, we're gonna have to go over logs and the logarithmic stuffs. But I think, as an intro to growth and decay, this is a good place to stop. But yeah, this has been applying exponential functions. Yeah, don't worry, we'll get into this stuff on how to solve for exponents on the other side. But until then, that's all for this one, and I shall see you in the next one.